Hi there, welcome to your lesson on interpreting mathematical models. Recently we've been looking at all kinds of power models, specifically quadratic power models and cubic power models. Both of those are very important curves or models used in real life to represent many real-life phenomena. Let's begin with a problem about this great sport, the great sport of shot put. So here's our situation. At a school sports day, Petra has to throw a shot put. The path of the shot put follows a parabolic curve given by this equation. So here's the equation we are given, where t is the time in seconds, so what would normally be the x value, or the horizontal axis, that's our t value. That's the time in seconds that has elapsed since the shot put left Petra's hand. F of t, right here, which would be like our y value, or our vertical axis, that represents the height of the shot put in meters above the ground. Question A, find the height of the shot put after 5 seconds. So what would that be? Well, by being told that the height after 5 seconds, we're being told that the time is 5 seconds. So it's saying after a time of 5 seconds has passed, how high is the shot put? So we can just take that t value of 5, put it right into our function, which we see here, and also here and here. Every t is replaced by 5, and that means what is the height at a time of 5? And that's what we can find here. So what is it? Okay, that height is 3.9375 meters. So hopefully you're able to punch that in correctly in your calculator to get that value. So again, the height at 5 seconds is this. Okay, so this can also be done on our calculator, not just by entering these numbers here, but also by using a feature in our calculator. So let me just remind you how to do that. If you enter the function first of all, so let me do that now. Okay, so I entered the function here. You don't see the whole thing, but I entered the whole thing. I can put graph, for example. I can see the function appearing there. But the way to find y values, because that's what we need the y value when the x value is 5. Okay, so t is like the x. So we can just go to second, and we've used this before, I think, calc number 1 value. And we're saying when the x, or in this case the t value, is 5, so when we have 5 seconds, it's going to tell us the y value. Let's check. 3.9375. It found the point for us. So it matches what we get when we put it into the model here. Okay, so that's a simple question. Let's look at B now. Find the times when the height of the shot is 3 meters. So this time we're saying when is the height 3 meters? Okay, so f of t, which represents the height, like the y value. So this is like saying when is y equal to 3. So we can replace that part of the function here. 3 equals that. This can be solved using some algebra, of course, but in this course we don't have to worry about the algebra for this kind of solving. We can just go straight to using our calculator. So on our calculator, how do you enter this? Well, you can think of it as two functions, because it's saying when is this function equal to 3? So it's like when is a function that's y equals 3, a horizontal line y equals 3, when is it equal to this function, which is the function we have? So you can enter it as in your calculator as y1 being this one, y2 being this one, or in my case I already entered this one, so this can be my y2. Enter both functions, and you're trying to see when is one function equal to the other. Because when you find when those two functions intersect, you will have the answer to when is the height 3. It'll make more sense also when we see the actual diagram, but for now, enter both of those, and then you can graph them together, and then you can find the intersection by doing second calc intercept, right? So do that, find the two intersection points. All right, so your graph can look like this. So here's the quadratic that models the shot put, and here's the line y equals 3. So that's what we're looking for here when the height is 3. So here's the height at 3. And the height at the shot put is at a height of 3 here and here. And those 2 points can be found with the calculator by finding intercepts, right? Those happen to work out to be even numbers in this case, x equals 2 and x equals 10. So I hope you're able to find those 2 points of intersection. But this problem kind of highlights an important application of our calculator, but also just application of solving equations. When we have this kind of situation, think of it as two curves, the curve and then the horizontal line, and that allows you to find specific values when y is a set value. Okay, let's look at another one. So here, this shows obviously something the whole world is dealing with right now. It's about a pandemic. So we have a pandemic which can be modeled by this equation. This time it's not quadratic, it's cubic. and x represents the number of weeks after the outbreak started, and f of x represents the number of cases reported. So this is going to be, the input is weeks, and the output, the y value, or the f of x value, is going to be how many cases we have. Okay, here's the questions we have to answer regarding that. So first of all, plot the graph between x equals 0 and x equals 50. So in other words, when you enter this on your calculator, then change the window to be something between 0 and 50. You don't want to see beyond that on the window. So let's try that to start. And once you've done that, answer, does the graph have a local maximum and minimum value? So look at your graph and think about it. Does it have a maximum or minimum? Okay, so here's the graph. Here's between 0 and 50. And you can see clearly it's rising very quickly. So as the weeks go by, the cases increase rapidly. And the answer to local max or minimum, no, it doesn't. You can see it's one of those cubic graphs. We talked about these in the last lesson. These cubic graphs that have no max or min. So it's one of those. Now C, find the number of cases when x equals 20 and when x equals 40. So basically that means putting 20 into the function and then putting 40 into the function. So if you put 20 into the function, we can write it like this. So 20 is your input. It goes into this x value as well. And then you can calculate that to be this value here. So try the same thing for 40. How many cases will there be at week 40? Okay, here's the answer for that. 40 is our input. We calculate it and we get this many cases. So it's rising very quickly. All right, and now state whether this is a suitable model for this scenario. Do you think this equation, looking at the graph, is a good model for this pandemic? Well, maybe you answered something like this. No, it's not a good model, not suitable, because the predicted number of cases will keep increasing forever and actually increases very quickly as the weeks go by. And in a true pandemic situation, this won't happen. Eventually it'll plateau. Maybe there'll be a decrease in cases and so on, but it shouldn't keep rising like that forever. At least that's our hope, right? Okay, let's move on to another kind of classic problem that we have when we deal with cubics. Okay, so we have what we have here is an open box. It's made from a piece of cardboard, let's say. So here's a piece of cardboard that measured 12 by 10 centimeters. And then there were squares of side X which were cut out from each corner. So we started with a rectangle and then the corners were cut out and those are squares. And those are squares, it says, of side X. So let's say there was a square there, we cut it out. It was X by X, so it's cut out. And it's cut out like that in every corner. So what that tells you is that this length is X and this length is X also. So now if we fold along this edge here and also here, if we make that fold right here on every side, we can then fold these sides up and then imagine having an open top box like this. So imagine these four sides here, again, were folded up. Then we have this box. And this box has a height of X because imagine if you folded this up, then the height would be X. So see if you can imagine that height being X. Now the next question though is, how long is this side here? So now that these two little squares have been cut out, how long is this? If it began as 12, how long is it now? Well, I hope you came up with 12 minus 2x, because this whole length was 12, but then we took off an x bit here and an x bit here, so it's 12 minus 2 x's. All right, so that's how long from here to here. Now do the same thing for, and then we have that on the box there. So if you folded that up, one side of the box would be 12 minus 2x in length, because that would be exactly one length of the box. How about this other side? How long would this be here? Okay, so that's 10 minus 2x. The same process, 10 minus the 2x's, we get that length here. So now we know when we fold those, the box has these dimensions, 10 minus 2x, 12 minus 2x, and a height of x. So next question, what's the equation for the volume of the box in terms of x? So write a volume equation for that. Okay, maybe you came up with this. Volume is found by doing length times width times height when we have a box shape, right? So those two bottom parts multiplied and then multiplied by the height. So there's our volume in terms of x. Okay, let's continue. So there's our volume formula. Next question, what are the x-intercepts? For this equation here, what are the x-intercepts? Well, you may remember when we have a equation that's factored like this, we can set each of the factors equal to 0 to find the x-intercepts. So this set equal to 0 is 0. Next one, 10 minus 2x, set it equal to 0, solve for x, and you get 5. Last one, set that equal to 0, solve for x, 6. So now we know our three x-intercepts are these numbers. Okay, let's do that on our calculator also. So enter this equation on your calculator and graph it. Graph it, and notice that you'll have those three x-intercepts. You might have to change the window a little bit to make sure you see the whole graph. So change the window as you need to. And then find the maximum point. And remember, for that we can do second calc maximum. All right, let's check. So here's the graph, and when you looked for the maximum, hopefully you found this point right here, 1.811 and 96.771. What does that represent? What do those two numbers represent? Okay, so what do these two numbers represent? Well, this is like our x value, which is the x value in terms of our box, and this is our y-axis, which in this case is a v, so that's the volume. So this represents the maximum volume of 96.7 when x is 1.811. So when those little squares are 1.8 by 1.8 that were cut out from the corners, that will give us our maximum volume for this box. Okay, next question. When is the model valid? In other words, is this model always valid for the volume of this box? Okay, this question is a little trickier. No, it's not valid always. It's only valid between 0 and 5. That means x values can only be between 0 and 5. And that makes sense here because we can have 0 height here, sure. That's x value of 0. And then maximum x value is 5 because when you put 5 in here, you get 0 for this length. If you go anything beyond 5 for x, this is going to make this value negative, and you cannot have a negative length of this side here. You can have a 0 length, but you cannot have negative. So this model is only valid between 0 and 5, and that happens often in mathematics, where we have a great equation to model a real situation, but the graph or the equation is not valid for forever. Only portions of the graph or model are valid. So in this case, our domain is 0 to 5. It's valid there, but beyond that, it's not valid for our situation. Okay, try this question. It's very similar to what we just did. First, to begin, read it, draw a diagram, and see if you can find an equation for volume like we did in the last problem. Okay, volume should be that. Check your work carefully about the squares being cut out from the corners and all that. So there's our volume. Now we're going to plot the graph and find the x-intercepts. So here's the graph, here's the x-intercepts. Okay, D, what do the x-intercepts tell you? Well, what do they tell you? Okay, the x values must be between 0 and 3. So just like we had here, if you go beyond 3 for x, this will become a negative number, and then it's not valid anymore. Okay, what's the maximum minimum points? They are these values. Hopefully you could find those on your graph. And finally, please read what it says for f. Okay, let's talk about cats. Cats are great. Cats love food, and cat food often comes in cylindrical cans. So we're going to do a problem about a cylinder, but before we start, we should recap some things we know about volume and surface area of cylinders. So flashback. Here is a prism. It's not a cylinder, but to find the volume, we always do base area times height. Imagine just stacking things like that. So base area times height. You're stacking it up. Volume is base area times height. Okay, it's like saying how many bases do we have stacked up. All right, volume of this one also, base area times height. And in this case, it's the area of a triangle times height. Works the same way for a cylinder. If we want the volume, we do base area and we stack them up. That tells us how many we have of those bases. So base area times height. Base area times height. And for a cylinder, a circular base has an area of pi r squared. So to find the volume, we do pi r squared times height. That's our volume. Okay, surface area of a cylinder. We have this distance is called a circumference, 2 pi r. That distance is here. Imagine you unrolled the center of this cylinder. It makes a giant rectangle, and it has the same length as we see there, 2 pi r. The height of that is, of course, height of the cylinder, so that goes here. So that's the area of that, and then we have two circles, and circles have an area of 2 pi r squared. So our whole surface area for a cylinder is 2 pi r squared, two circles, plus this rectangle, which has an area of 2 pi r times h. So that's the formula for surface area of a cylinder. Now we're going to apply it to this problem. Please read the first part here and answer A and B. Work. So beginning with volume of a cylinder, we can substitute the 200 for volume that we know, and we have that. Then you can rearrange that and solve for h. Okay, now try C and D. Read those and try those. Okay, our goal here is to make a surface area formula, but to make it only using one variable. So we're going to take that h, replace it with what we found here. So we make the replacement, we get that. That can multiply and simplify into this. Now finally answer this question. You've graphed it, so check your graph. There's the minimum point, which is the minimum surface area.